Hey there guys and gals, welcome to Deep Intuition video number 1, Pointers. It's me Nirex, and let's get right into what this is all about. So, I do have a video about pointers on my beginner C++ series, which is kind of bullshit, okay? It just teaches you the concept of a pointer in a very childish manner. You know, it's boxes and symbols and, all colorful and good. But in today's video, we're going to actually jump into the assembly and see how things work. So we're going to go ahead and see what they are, what the symbols mean, how they're mapped to memory, different types of pointers. And this is the biggest thing. This is the topic that's going to take the most of the time in this video. It's going to take up a lot of time. Okay, so let's jump into it. Now, let's go ahead and see exactly what they are. So these guys, the pointers that I have taught you about, you should already have an idea of what pointers are. So, just a little bit, the boxes and the colorful bullshit. So these are variables that hold the address of another variable within themselves. Okay, so wherever I is located in your memory, pi will have that address in itself. Int pointer means just a pointer to that guy, so it doesn't hold an int, it holds an address of an int, and the offset. All right, so that's basically what the pointers are. Okay, that's exactly what they are. We're not going to go over the applications of pointers, just what they are. All right. Now, what the symbols mean, they're pretty goddamn easy. This guy means, when you put this guy right here, it means you're creating a pointer. When you put it, when you're accessing the variable, it means you're dereferencing the variable. And this means the address. So let me just go ahead. Yeah, don't mind those little guys. It's just for later explanation. So this guy, after type, means creating a pointer. Before name, no type, means dereferencing. This before name means the address of a variable, and the address means location in memory. Alright, so we're basically just trying to work with locations of memory. We take some location, we do them, we do whatever we want with them, we put them back, we do all that kind of bullshit. Alright, so if this guy comes before the name without any kind of type, it doesn't have an int, it's not, like no bullshit at all, it's dereferencing. If this guy comes before the name, it's giving us the address of that variable, and the address means the location in memory. Alright, so now with all that bullshit aside, let's get into how they're mapped to memory. So let's say we have something like this. Alright, and these are our memory units. These are each one of these is a byte in memory. Alright, these are little boxes that can hold 1 byte of data in themselves. This is the exact way memory is mapped. Well, maybe not the exact way, but this is the representation. 1, 2, 3, 4, 5, 6, 7, and 8. Yeah, 8 should be enough. Let's actually make 4 more just because. Alright, so whenever I'm creating an int, let's say int I will occupy 4 of these units because it's 4 bytes. So these will all hold whatever is in I, right? And this guy will be the beginning of I. So int I equals 10. These guys will hold the value of 10 with a bunch of zeros just indicating, is it 10 and where is 10? Is it 10 million? Is it 10? Whatever it is. It's just a 1 with a bunch of zeros. Or, better yet, they're just going to hold the value of I within 4 bytes. Alright, we don't care if they're going to be null, we don't care anything, it's just going to reserve, maybe it uses just 1 byte of it, but it's going to reserve 4 bytes. And that's it. Now, if we create a pointer to I, in pointer p of I, what am I doing? Which is going to be equal to the address of I. Now this will hold the address of I. Let's say this guy has an address of 1000. So pi will first off occupy these 8 guys, okay, in a 64-bit environment, because 64 bits, well, we're on 32-bit, but 64-bit means 8 bytes, and this guy is gonna occupy 8 bytes. And in this 8 bytes, it's gonna hold the value of this guy. So 10 will be something like this. So 1, for instance, 0. It's not exactly like this, I'm just representing it, okay? And it has an address of maybe, what am I doing? OX8430, I don't know, 2014 or I don't know, 429, something like that. This guy will hold that guy right there, which will be the beginning address of exactly that. Alright? So this guy will hold that. We have 8430429 Alright, and that's basically it. So this guy has the address of that, and this guy will hold the address inside memory like this. So whenever we are trying to dereference the pointer, we use the value within it and act as if that value was an address in the memory, and then go to that address in the memory and then take whatever value was in there. Alright, and that's basically what it is. Okay? So maybe I should put 10 like that. 10, or no, 10 should be like this, or you know, any other way. Doesn't really matter. You could put it like that. It's a little bit different, but it doesn't really matter. It's just representation. It's not the real world scenario. It's just the representation. Now, pointers in 32-bit environments, of course, they occupy 4 bytes. In 64-bit, they occupy 8 bytes. It doesn't really matter. We could just check them out right now, but yeah, let's actually do that just to prove to you that I'm not saying anything. You could always trust me. So let's go size of an int pointer, which is going to be now this guy is obviously gonna give me 4. So there we go, 4 bytes. Now if I was to run it on this guy, it would give me 8 bytes. I'm not gonna, because it's just a pain in the ass. So yeah, and that's basically it for how they are mapped in memory. Now if I was to make an array that has 2 values, 2 elements, they would just occupy, let's say, if I was to make pointers to each one, the pointers would just come after each other, or the elements would come after each other. So it's like an 8 byte here and an 8 byte after it. That's basically how it works. Now let's talk about the deep intuition part, different types of pointers and how they are mapped in assembly. Alright, so without further ado, let's get right into it. Now, I put a breakpoint here just to see all the bullshit, and don't mind these guys, they're just random shit. Now let's get right into this assembly. Alright, so these are the assembly codes. If you don't know them, you don't really have to. This video, this is just for people who want to gain a whole lot of information about pointers and how they work. You don't really have to watch this video if you don't want to. This is not the application of pointers, that's another video. Okay, so this is where our bullshit starts. Okay, this is int main. We all have all this bullshit before the application starts. We don't give a damn about them. And this is where our pointers in memory. Alright, so int I equals 10. We create an integer. We create a pointer of type dword. Double word means 4 bytes, size of an integer. And we put this value 0a h. H means hexadecimal. So we put this motherfucker into the address of I. Alright, this means the effective address. So, well, yeah, kind of like that. And we put that in there. I mean, this is not, well, I'm explaining it a little bit bad, but yeah, we're basically pushing this guy in there. So we're moving this asshole into that asshole. Okay, and now we're gonna go ahead and create a pointer for that. So int I, and I'm sorry, I can't really zoom this guy in for some goddamn reason. Let's see if I can, oh well, doesn't really matter. So now we're gonna go ahead and see what the hell's up. So let me actually do something here real quick, just so you guys can see it better. Oh, there we go. Okay, so pointers in memory should be, yeah, right here. Pointers in memory, we're going to have an I. We're going to push this guy value into this guy, all right? Into the I, the effective address of I. And then we come down here. In pointer pi equals the address of I. So what's going to happen here is we're going to push the effective address of I into EAX. Okay, load effective address of I into EAX. And then we're going to move EAX, which had the effective address of I, into PI, the pointer that we made, as a dword type. Okay? And then we're going to dereference that and add 20 to it. So already we have made a variable, we've made a pointer, and we're going to dereference that and add 20 to it. Okay? So what's going to happen is we're going to add the effective address of PI, which had the EAX in it. We're dereferencing it, right? So we're adding this guy into EAX, then we're dereferencing EAX and putting it into ECX. All right? Then we add 20 to ECX, and then we move the effective address of PI into EDX, and then ECX into EDX. Okay, we reference it back, so the pointer is pointing back to the variable. And this is exactly what happens when you dereference something, add something to it, and move it back out. Okay. Now let's talk about references in memory. So these guys right here are the code in C++, and these are the code in assembly. These are the places in memory that are being executed at. All right. Let's talk about the references. Now references are implemented in different ways in different compilers, but they don't really have a standard that everybody follows. Okay, everybody creates them in their compiler in a special or specific way. So let's talk about this guy right here, int n equals 15. So we create another int called n. Right here we put 15 in it. All right, put 15 in this guy, and that's it. Now 15 in assembly is F, of course, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F, which is 15. So we put 15 into the effective address of n, we put 15 in there as a dword pointer, because dword 4 bytes, pointer like that. And then we create this guy, all right, we create an R, we load the effective address of n into EAX, we jam the address into EAX, and then we push EAX into an R. So they work almost exactly like pointers, all right? Under the skin they're pointers, but they're less messed up, easier to use. Now, you might have a question asking, what the hell is this? Well, these work exactly like pointers, but in assembly, all right? Whatever is in this guy is gonna, when you do this, it's gonna represent the thing that's in the memory of that guy. So int n equals 15 right here, this n is not actually an int. It's an address, and then we put this guy into that guy. Okay, so we take the location of that guy, and then we put 15 into the location, and then we do that exact same thing right here. And we take the address of that shit, put it into EAX as a load effective address, as an effective address, and then we push EAX, the effective address of n, into an R. Now this is assembly, you can't really, push this guy right here, it's shitty. So I hope it's not too confusing. I know it is, but yeah, you asked for it. If you're watching this video, it's your choice, okay? You don't have to, it's not a must. You can, you cannot, really up to you. Alright, now let's talk about pointer arithmetics. So I've created a character pointer and the pointer that we had up here, okay? So we're going to look at what plus does to the pointers. So we have a character ch, which is equal to c, putting 63 of hexadecimal into ch as a byte because it's just 1 byte. We move that there, and then we do the same thing we did with this guy right here. Okay, this guy right here. Where is it? Yeah, this guy. So we create a pointer, load effective address of ch into EAX, and then we put EAX into PCH, which is this guy right here. And then we want to add 2 to the ch, okay, 1 to ch, which is just a simple character. It's not a character pointer, it's just a normal character. We're going to see the differences. So the way they differ is that they look almost exactly the same, okay, but almost the same, not exactly the same. So we move this guy, okay, into AL. We move the pointer, we move the effective address of a pointer into AL, and then we add 1 to that guy, and that's it. That's basically it, and then we move back that AL into CH. So we bring it into a register, we add 1 to it, and then we push it back into the pointer, into the variable that we have had. In the next one, we are adding into the pointer itself. We're not adding to the value of this guy. We're actually adding the pointer. We're going to see the differences. So here we use a D word instead of a byte, because byte means 1 byte, character is 1 byte, D word for 4 bytes, int is a 4 byte. We're going to move this guy into EAX, and then we're going to add 4 to EAX, and then we're going to move EAX back into this guy. So the only difference that we can see here is that we are adding 4 instead of 1 because it's a different thing, but because they have the different sizes. This guy is bigger than this guy, okay? So also we're going to use a bigger register. AL is a smaller register, EAX is a bigger register, so obviously we're going to use extended accumulator register. And that's basically it for arithmetic bullshit in assembly. Pointers work like that. They just add bullshit to each other and they point to another address in the memory. This adds the value, this adds 1 to the value, this adds 1 to 4 to the thing, to where the pointer is pointing to. But the thing is, we're both adding to the value of these guys. Okay, that's why I wanted to put this guy right here as a normal variable and this guy as a pointer variable. They look exactly the same. Just some of the things are different, and they're not really that big of a difference anyhow. Okay, let's get into array bullshit. So I've created an array here, int r equals this guy right here. So it has 10 elements, all right? 10 elements of type integer, so they're each 4 bytes. And if you look at here, we move 1 to this array, number 1, we move 2 to this guy, 3 to this guy, 4 to this guy, and it's all the effective address of these guys, all right? And so R will be the index of this dude right here. Whenever you call R, it's going to give you a pointer to this guy. Now, if we add this, which it means that we are adding 1 to that guy. So this guy is an EBP. We negate this guy from that and we get this index. Just some bullshit calculations compiler has done for us, and so on and so forth. We get all the elements of our array like this to this point, and as you can see, they're moving up 4 by 4 in our memory. Okay, so negative 74, negative 70, negative 6c, negative 68, negative 64, and so on and so forth. And so that's basically it when creating an array in assembly. Just creating pointers, D-word pointers, D-word because it's an int, pointer because arrays are basically pointers, just a list of pointers in memory with one pointer pointing to where the array starts, or the beginning element of where the array starts. So the very first byte of where this whole monstrosity begins. Okay. So that's been it. Now let's talk about this guy right here. Int pointer pa1 equals this guy right here. So what we're going to do is load the effective address of array, which is the first element of this guy, the 0th element, into EAX. So we're just going to jam this guy into EAX, and then we're going to push EAX. Let me just delete that because they're the same dude. And then we're going to push EAX. We're going to push actually EAX into the effective address of PA1, which was this guy here. So they're pretty goddamn similar to each other, like what we saw up here. So they're really similar to each other. Nothing to be worried about, nothing to be scared of. This is exactly how it's done in memory, and nothing too big. Now we also have this guy right here. So we're going to take the address of the 5th element, 0, 1, 2, 3, 4, which will be 5th element of the array, into another pointer. So this guy is going to be pointing to 0, 1, 2, 3, 4. This guy is going to point to number 5 right here. So what's going to happen here is that we're going to move this guy into that guy. All right, we're going to do we're going to move 4 into EAX. Alright, 4 goes into EAX, then we shift to the left in EAX by 2. So 2, 4. We shift 4 times to the left, and we'll actually shift 2 times, but it gets multiplied by 4, the value inside this guy. Alright. Then we load the effective address of EAX, just calculating random bullshit for where we should actually point to. Then we put the effective address of array of the index EAX into ECX, just another register, and then we load effective address here, and then we move this guy back into PA2, which was our variable right here. So now this way we have calculated a reference, the address of this guy right here. Now let's create another pointer, put it to 10. I'm now putting the value of this guy to 10 using this the pointer variable I've made here. So first off, we push this guy into EAX. Alright, we move this dude as a dword pointer into EAX, the effective address of it. Then we add 0A, which is 10. Okay, A is 10, so we move 10 to EAX, where EAX is pointed to, and it's the same thing right here. We could have also just done this, not quite, but you know. This is basically what's happening. We need to dereference it. If it was a normal value, we probably would have done it like that, but it's not, so we're going to do it like this. Now PA1, fifth element is going to be equal to 15. So again, we do this bullshit right here. We take this guy right here, pointer of PA1, and ECX plus EAX, we calculate the where this guy is, we calculate the location of this guy in the memory, and we put 50 in it with the move command. That's basically how it works. Let's talk about the distance. So the distance is 2 pointers divided, subtracted from each other. So the way it's done is we move this guy right here, PA2, into EAX, and then we move subtract PA1 from EAX, then we divide it kind of by 2. It's not quite the division, because division is kind of tricky in assembly. It's very tricky actually. So we just calculate the number of bytes, because if we just do that, it's going to give us the number in bytes, but we want the number in elements. This is basically what's doing that, okay? And then we push that into, we do that into EAX, SAR. We're going to talk about that. And then we do EAX, we push whatever was in EAX, which is this guy, back into our dist variable right here. So that's how we calculate the distance of 2 pointers. Okay, now let's get into the hard parts. We have pointer to pointer 1 and pointer to pointer 2. We have, what else do you have? You have random bullshit and random bullcrap, all that good stuff. Yeah, so let's talk about pointer to pointer. And yes, you can create pointers to pointers. And as I've already told you, if somebody's calling you a 3-star programmer, it means you're using this right here. And if you're using this, then that's not a compliment, okay? If anybody calls you a 3-star programmer, they're not complimenting you. All right, now let's talk about this guy, pointer to pointer. So we have an integer type named XX, and we're creating a pointer to that integer. So we're basically just loading the effective address of XX into EAX, and then it's just easy peasy, right? And then we're moving that guy into the pointer. It already should be second nature by now. Now we're creating another pointer, PPXX, and pushing the address of our last pointer, PXX. So this is a pointer to pointer. We're going to put the address of a pointer. As you can see, it's identical to that one. The only things that change the variable names, but the rest, they're exactly the same. dword pointer, because it's a 4-byte pointer. The offset is 4 bytes, easy peasy. We just push that there, and that's all there is to pointers. If you put 10 million pointers there, 10 million stars here, and 10 million minus 1 stars into the next one, and then give the address of that one to this one, then it's just going to be the same thing. Okay, so let's talk about pointer to pointer 2. Okay, this was the easy one. Now this one's the little bit more difficult one. So we have an integer, x, and we have a pointer. We have a pointer, and we're giving it the address of x, easy peasy. You've already seen it 10 million times right here. We have one more of these guys. No, easy peasy. We have one more of these guys. Again, easy peasy, not that hard. Now let's talk about the array right here. So how do we do that? We're going to dereference this guy 2 times just to get a simple int pointer, and then give it the address of array plus 5, which is just evaluates to 5 times 4 because it's an int. So let's do that. So we are having this guy right here, okay, dereference of PPPX. So 3 p's, 2 dereferences, which means it's an int pointer. Right, one of these p's remain, so that's 1 pointer. Still 1 pointer. So we're going to give the address of R to this guy right here, which is quite simple. So EBP minus 64, as you have seen right here, minus 64, which is here. It's just optimization. It's all calculated. We add to this guy, we add 5 to that guy. 1, 2, 3, 4, 5, or rather 0, 1, 2, 3, 4, 5, which is exactly this guy. And we come down here. Let me find the next. Yep, right here. We add this guy, which is exactly this guy, as a load effective address. We jam the effective address of this guy into EAX, and that's basically what happens. So we've already calculated what this is. Now, PPPX as a D word, we dereference that because there's one of these guys. So we dereference that, put it into EAX. We dereference that, put it into EDX. And then we have that whole bullshit right here, which was stored into EAX, and we put EAX into the effective address of EDX, which is the dereferenced version of our PPPX. Whew, I'm sorry if it was confusing, but this is exactly how pointers work. Alright, now this is one of the examples that is absolutely hard to get, okay? You won't see it very often. So let's talk a bit about this guy now. We dereference it 3 times, give it a value. Let me just take this guy away because they're the same thing. So let's talk about that. How do we do this? Well, we dereference it once, twice, thrice. So that means all these go away. Basically, x is equal to 5. So first off, we put this guy into EAX, we put this guy into ECX, we put this guy into EDX. Alright, easy peasy. And then we put this guy back into EDX, and there we have it. So we basically just go 3 levels deep to get the exact value, address of EDX where this guy is ultimately pointing to, and we put 5 in there. So there might be a question that you might be asking. Okay, so question is, we only have so many registers at our hand. What if this guy is like 5 or like 50 levels deep? What then? Well, let me just answer that for you right now. XP, or rather, yeah, let me just do something like that, which is gonna be, this is gonna be a bit painful to write, but don't worry about it. We can do it quite fast. Okay, this is going to take a long while, so let me just go ahead and create a 5-pointer variable. So pointer to pointer, it's going to be 2 pointers. It's going to be having 3 pointers, 2 pointers, 1 pointer. So this is going to be XP, XPP, XPPP, 4 P's and 5 P's, and it should be done. And we have an int xz. So this is going to be equal to 1. This is going to be equal to the address of xz. This is going to be equal to the address of xp, and so on and so forth. xpp, xppp, xppp, yeah, like that. And what the hell is your issue right here? Ah, yeah, the equation operator. Alright, so that's basically what we need to do right here. Now let's go take a look at the assembly of this guy right here, see exactly what happens when we're talking about that guy. So if I take this guy, I'm just going to push it back into my Notepad++ because I don't want to, just hurt your eyes. Okay, so we have this guy. We create a variable, put this guy into the effective address of EZ. and we have XP. We do that to XP, EAX, 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 EAX. All right, so that much is obvious. All right, but let's say I wanted to do something like that. 1, 2, 3, 4, 5 of this guy is equal to 2. All right, this is the question. So that much was obvious, but this guy right here is the question. So EAX, ECX, EDX, EAX, ECX. As you can see, ECX being used 2 times. But how does that work? How, is the address not lost? Is it not messed up? So let's calculate and see exactly how it works. So we push the address of this guy into EAX. Then we put EAX into ECX, ECX into EDX, EDX into EAX, and EAX back into ECX. Alright, so we're using this guy twice, but it doesn't really matter because we haven't lost that. This is already been gathered. So if we're going more than 4 registers, and yes, it's 4 registers, we're just going to reuse them one by one. So we put EAX into ECX, and then we put, what was it? Yeah, ECX back into EAX, and into EDX, and ECX into EDX, and just like that, we go forward and we create all that bullshit that we want to create. So we just use these guys again and again, like the example you're seeing here. But the thing is, the effective address is not lost. We've already stored it in ECX, then we put ECX into EDX, then EDX into EAX, then EAX back into ECX. So it's already there. Next step would be to do what we do. We added 10 more, it would just work using this formula. And that's basically it for using a whole lot of pointers and exactly how they work in memory. Now let's get back into this guy right here. So this was a simple pointer to pointer to pointer. Now let's talk about the struct of size. Okay, so struct of size 20, bullshit, BS. So I've created a struct right here. Random bullshit struct. Alright, it has 1 function and 5 integers, all of which are of size 4, and all in all, this guy is going to be of size 20 because of these motherfuckers right there. So let's see how it works. Now we have a struct of size 20 right here, and we have a function. So let me just go look at the code. We have a function, random bullcrap. We have a struct of size 20. Let's look at the struct of size 20 first, how it works in assembly. It's not showing me anything because it's not really doing anything. We're not initializing it, so we don't give a damn about it. But there is one right here where we actually initialize the bullshit. Where was it? Let me just find it. Yeah, right here. We actually do that with the crowbar bullshit. So we don't give a damn about that, but function. Let's talk about the function of random bullcrap. So random bullcrap is a function that I've made that takes a random bullshit reference and then do that. And then there's a normal random bullcrap, which takes a normal random bullshit. It's not just a reference. Alright, so let's talk about this one first, which takes a reference. We put 14 into EAX. Now 14 evaluates into 20 because the size is 20, of course. Then we put 0 into ECX, multiply 0 by ECX just to calculate which one we are using, just to get the index of that guy. We're using the 0th element. If I was to put it to 2 and then do it again, let me just go ahead and do that, just to show you what exactly that imul is doing right there. So we do that. We don't give a damn about that. Oh yeah, there we go. Yeah, it's gonna change a little bit. That's we use that one right there because it's a bit different. But here we're calculating it with a shift command instead of a multiply command. So it's the same thing. It's gonna just work the way it does. But here we use the multiply just to get this guy right here, the 0th element, load effective address of this guy into EDX, push EDX into stack, and then we have this guy. So we call this function at this address, and that's it. When it returns, we put 4 into ESP, or add 4 into ESP. Alright, that's basically it. So it's really not that hard, maybe a bit more confusing than what we did back here, because it's now, we're not getting the function calls and kind of out of pointers, but we don't really give a damn about that. Now let's talk about the normal random ball trap. So this is not really the focus right here. The focus is this guy right here. That one was just to trick the compiler into thinking that the variable has been initialized. So if I take this out, if I try to compile it, it's going to actually... Wait, it's not? Okay, that's nice. But anyhow, if I was to make something like that, if I was to say int on init, and if I was to use my init int, let's say int x equals on init, or int init equals on init, then we're going to have issues, right? So the one way to actually mess with that is to do something like that. So let's say void r int reference x. And all we have to do is do r of on init. Well, I put it before that, but yeah. So r of on init, now it all works good and well and dandy. But anyhow, we don't give a damn about that. We give a damn about this. Okay, so normal random ball trap of BS0. So first off, we're going to calculate what this guy is. All right. Up until here, let's see. So we go add 20 to that because it's the size of it. We put 0 into EAX, multiply EAX by 0 and put it into ECX, so it's index 0 of this guy. Put it into the ECX, and we do BS of ECX. BS is the name of that guy, remember? So we do BS ECX, we put that element into this guy, we do the effective address of that guy, and then we subtract 20 with that from ESP. I don't know why ESP came into play, but yeah, it came into play here. Okay, so we do that, then we move this guy ESP into EAX. Alright, so we're using EAX again. Now, all these guys happen. These are all the ints that are in the bullshit. So dword, 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 dword. I had 5 ints. There are 5 dwords right here. All the ints that are, EDX, EDX plus 4, EDX plus 8, EDX plus 0C, EDX plus 10. That's basically, we're just creating that. Then we call the normal bullcrap in this address, and then we push, or rather we add 20 to ESP. 14H is just 20. And so that's basically it for normal random bullcrap function, which is a normal function that takes a random bullshit struct. Alright, if I was to do something like that, if this wasn't an array, then this guy probably wouldn't have happened. Definitely this guy wouldn't have happened, and you would only see this guy. So this is just calculating which one of these elements to put there. Now let's talk about the last one in my list of shits to tell, which is the crowbar one. So we have a normal array, alright, right there, which is just bullshit, alright, and then we call one of these guys' function, alright. So there's a function here, there's an egg there, there's a function here, and this is gonna actually add 10 to the egg. I don't know what's the relation to a crowbar, but yeah, get used to it. So let me just add a couple of these guys right here. Let me check. Okay, this doesn't seem to be complete because it has to actually be a lot more than that, I think. So let me just do that again. Alright, yeah, it's not complete, obviously. Alright, so we're gonna just do it right here. Alright, so member function call. Let me push that there. Yes, this is the complete code. Alright, so we're gonna go member function call a normal array. So we have an array, and this guy, we're gonna call it on this guy. So we're gonna move 4 into EAX. Why 4, do you ask? Well, it's obvious because crowbar had an int in it, of size 4. So we're gonna add 4 into that guy. Then we're gonna put 3 into EAX. I'm sorry, multiply EAX by 3, which is the size of the thing that we're gonna go for, which is, the size of this guy itself is 4, right? So we put 4, we move 4 into EAX, then we multiply EAX by 3, which will give me 12, and 12 is where CB3 is residing at. And then we load effective address of whatever is at EAC into ECX into ECX. So whatever is in here, we don't give a damn about it, we just load the effective address in here. Alright, and CB is just the name of this guy. So CB at ECX's address will load into ECX again, and we then call this guy right there. Calling is a bit different. It works on what's in each register, and then it works with registers to bring the output back, bring the return back. And that's basically how call works. So crowbar boil will be called. This is just some Visual Studio bullshit. The way you call it is actually just like that, and it works with jump functions and all that random bullshit, assembly bullshit, but we're not gonna go in there. So this is basically how it works in there. And these guys right here, these are the real world representations of how memory works. So 1, 2, 3, 4, 5, 6, 7, 8. As you can see, it's an 8-byte variable, 8-byte object or 8-byte number that represents which bullshit, which house, which unit of RAM we're actually at. And so that's basically it for this video. I know it was confusing. I know you may have thought that you probably wasted your time watching this, but yeah, don't feel so bad about it. I know this part right here, this part was probably one of the worst things, one of the nightmares of each programmer to be explained to. So yeah, I know everybody has a nightmare of, you know, having to sit through this for a second time, but yeah, I hope you enjoyed it. So anyhow, this has been it for this video, the deep intuition into pointers and, well, maybe just a little bit of assembly. So in this video you've learned exactly what pointers are, what each symbol means, how they're mapped to memory, and different types of pointers, and a little bit of assembly, just a bit, okay, just a tiny bit of assembly to see exactly how it works. Anyhow, if you have any questions, write them down below in the comments. If you like this video, do leave a like, and if you really enjoy this video, subscribe to the channel for more content. Thank you very much, and see you in the next one.